This is part 2 of the section 3.5 demo. Okay, so we have a system of linear differential equations written in matrix form, and we are being asked to rewrite it as two separate equations. So that says x prime is negative 2x plus y, and y prime is 0x minus 2y. Okay, we want to solve the equation that is autonomous using separation of variables. And we're going to name the constant of integration y naught to reflect that it's always the initial condition. So, okay, y prime, that's dy dt equals negative 2y. You might be able to write the solution down to this without doing any work, but I'll do it out just for fun. So I'm going to divide both sides by y and multiply both sides by dt. So you get 1 over y dy equals negative 2 dt. Integrate, ln y equals negative 2t plus c. Raise e to both sides, and you get y equals e to the negative 2t times e to the c. And then e to the c is the new constant of integration. And we get y equals k e to the negative 2t. And then this is what this sentence is about naming the constant of integration y naught. If you plug 0 in for t into this general solution, you get k. So they're saying instead of naming it k, let's call it y naught, y sub 0, to reflect that it's always the initial condition. So y of t is going to be y naught e to the negative 2t. Okay, in the non-autonomous equation, the x prime equation, we're going to replace one of the variables with the solution we found in part B. We'll replace y. So x prime equals negative 2x plus, instead of y, we have y naught e to the negative 2t. And then we're supposed to use linearity to solve the resulting autonomous, non-homogeneous equation. So that's the three-step process, linearity. The first step is to solve the associated homogeneous equation using separation of variables. So that means we want to solve dx dt equals negative 2x. The solution to that should be x equals constant times e to the negative 2t, but we're going to call the constant x naught this time. Again, to reflect the fact that k will always be the initial condition, x naught. All right, so we like to call this y homogeneous to remind ourselves. All right, now we're supposed to use lucky guess to find y, x particular for the non-homogeneous equation. And a good guess is alpha t e to the negative 2t. Your first guess was probably going to be alpha e to the negative 2t, and it would fail. So I'm trying to save us some time from a failed guess. So x particular is alpha t e to the negative 2t, and I need to plug it into the x prime equation, which means I need the derivative. So xp prime, I'm going to have to use the product rule. That's alpha t times e to the negative 2t. So it's first alpha t times the derivative of the second. The derivative of e to the negative 2t is negative 2e to the negative 2t plus the second e to the negative 2t times the derivative of the first. And there's my x prime. So I can plug that into this equation. So I have 2 alpha t e to the negative 2t plus alpha e to the negative 2t equals negative 2x. So that's negative 2 times this, alpha t e to the negative 2t, plus y naught e to the negative 2t. Now the idea is we're trying to figure out what alpha is here. What is alpha? So Okay, I just noticed I'm missing a negative sign right here. Okay, when I multiplied those two terms together, I should have gotten negative 2 alpha t e to the negative 2t. Okay, that's good because I need this term and this term should cancel. Okay, so that means that alpha e to the negative 2t has to equal y naught e to the negative 2t, which means that alpha has to equal y naught, which means that my final x particular, we guessed it had the format alpha t e to the negative 2t, and we now know that alpha is really y naught. So this is y naught t e to the negative 2t. All right, so to add parts 1 and 2 to obtain the general solution, so x general is x homogeneous plus x particular. X homogeneous was x naught e to the negative 2t, and x particular is y naught times t e to the negative 2t. The solution in vector form, write the solution to the system in vector notation. Okay, so that means we have an x and a y. So x and y. X is x naught e to the negative 2t plus y naught t e to the negative 2t. And then y was y naught e to the negative 2t. Okay, it says, is your answer to part E the same or equivalent to this expression here? So it looks like they just factored out an e to the negative 2t from this term and this term, and they were left with an x naught and a y naught. And then the next term, they pulled an e to the negative 2t e to the negative 2t out, and they were left with y naught and 0 because this is plus 0. So yes, that is the same. The first vector in the solution contains x naught, y naught, which is the initial condition. And then the second vector happens to be an eigenvector associated with our single eigenvalue that's written in terms of the initial condition. It is an eigenvector, a special eigenvector. So if we wanted to find the particular solution for the initial condition y naught is 1, 2, it would be y equals e to the negative 2t. I'm working off of this, and I'm just going to plug in the x naught and the y naught. Times 1, 2 plus t e to the negative 2t times y naught, which is 2, 0. So what we saw in this example turns out to be true in the general case. So we were able to solve this because it was partially decoupled, but we actually can use this result in all situations. So if y prime equals ay is a linear system that has a repeated eigenvalue, its general solution has this form. E to the lambda t v naught is the initial condition, lambda is your one repeated eigenvalue, plus t e to the lambda t v1, and v1 is a special eigenvector of the system that you calculate with this little formula. So we want to return to our example that we just worked really hard to find a solution for, and we want to write the general solution just using the information in this box, not the whole partially decoupling and solving thing. So I need to find out what lambda is, and then I need to calculate v1. So lambda, I do the determinant of a minus lambda I. So that's negative 2 minus lambda squared minus 0 equals 0, and you get lambda equals 2 multiplicity negative 2, sorry. Negative 2 multiplicity 2. So we've got the eigenvalue lambda, and then I have to figure out what V1 is. V1 is a minus lambda I, and in this case lambda is negative 2, so a plus 2I times V naught. So a plus 2I, so that's a is negative 2, 1, 0, negative 2. 2 times the identity is 2, 0, 0, 2. All of that times the initial condition x naught, y naught. Okay, so my a plus 2I is going to be 0, 1, 0, 0 times x naught, y naught, which is y naught 0. So that's my V1. And then I'm running out of room. To write the final solution, I'm just going to plug it all into this formula. So y is e to the lambda t, e to the 2t, v naught, which is x naught, y naught, plus t e to the lambda t. Sorry, lambda is negative 2. Negative 2t times v1, which is y naught 0. So we were able to write this solution down doing way less work than we did using the system of the partially decoupled technique. And that's great. It saves us a lot of time and work in that situation, and we can use this technique even for a system that is not partially decoupled.